In this video, we're going to discuss waves. So, when we think about waves, we normally think of things like ocean waves. And while that's not a bad analogy, it's going to have to take quite a right-hand turn in order to apply to atoms, electrons, orbitals, and photons. Problem is, ocean waves are transverse. They travel over something. So if I have a bunch of particles of water, so we'll just look at the surface. Well, if you've ever tried to surf or just been on the water in the ocean and the wave comes in, you rise and you fall. You don't actually get pushed forward unless you're right near the shore and it's breaching. What happens is a wave comes. And what's really going to happen is, as that wave moves, as it tries to push forward, what it's actually going to do is it's going to raise the particles. Effectively, the front end of a wave is a rise and the back end is a fall. And it's going to pick up particles and make them do just that. And so these particles continue to rise a little bit. This one will rise more. This one will start to rise. The wave propagates through. As that wave eventually, starts getting further in, well, things that were on the backside start to go down. What we're actually seeing over time here is just the particles. Some go up as the wave moves forward. Some go down as the wave gets past them. And over time, what we'll see is that the wave starts to move through our material. The next one starts going up. The other ones that were still going up go up a little. The ones that were going down go down more. The ones that were at the peak start to go down. And our wave has gotten a little further along. This just continues. What the wave is actually doing on the ocean is it is drawing up the next molecule. And it is pushing down other ones. If you have a long sheet and you grab one piece and then start to grab the piece in front of it, and then the piece in front of that, and the piece in front of that, and the piece in front of that, you will move the part you're holding across the entire sheet. This is what a wave traveling through the water is doing. It is raising the next little bit and lowering the parts behind it. And so as the wave continues to travel, it will make one part of your water rise, one part of your water fall. But the water itself isn't moving anywhere. It's not going forward or backwards. It's going up and down. Now this is something that confuses us. Because if you're over here on the shore and you're watching, what it looks like is something is moving towards you. It looks to the human eye like something had started a long way away and is moving towards you. Now, this is important because if it's teeth and fur and claws moving towards you, bad. You should watch for that and hopefully get out of the way of it. But that is how our brains are shaped. We see the material move and we think it is an object because that is how we evolved to see it. But a wave through the water, it is not the physical matter that is moving towards you. All the matter of that water is basically where it originally was. But which part of it is pulled up, that is what is progressing towards you. Well, what is doing that? There's nothing under it. It's just a wave on the ocean. That is energy. The wave is energy. It's the energy needed to pull some water up higher to physically lift it up. But it also regains that energy as the other ones push down on the backside. And so it gets pushed forward a little as these fall, which gives it the energy to lift the next ones up. This is why waves can travel so far. They don't bleed a lot of energy as they travel through the water. They have to spread out for a long time before you don't notice them. Because they're not really wasting their energy. It's not like kicking the sand where it quickly runs out and doesn't seem to travel very far. The water just rises and falls. It regains its energy that it spent to rise when it falls. Transverse waves are things that we see a lot of. But standing waves are a little less common. These are things like guitar strings. If I have a guitar string and you pluck it, pull it down, what'll really happen is it goes down and then it will go back up. And so then the string will be up here and then it will go back down and then the string will be down here again and will go back up. It vibrates back and forth. It goes up, it goes down, it goes up, it goes down. We consider that a wave. The energy is radiating back and forth. The difference here is it's not allowed to move forward because it's trapped. On the ends are bounds that hold it. One of these might be the tie in a guitar, one of these might be your finger near a fret. Whatever it is, it traps that vibration. Well, there's a height you get to and a bottom. There's a distance on top and bottom here, and there's a length across this way. This has a wavelength. A standing wave is still a wave, and it has a wavelength. If you put your finger closer on a fret, you'll get a smaller one. Well, if you play guitar, bring your finger down and you get a higher pitch. It's a shorter wavelength, a higher frequency. We pick up higher frequencies as high-pitched sounds. Standing waves are still waves. Why we bring it up here is because this is what electrons are. Well, light is a transverse wave and can flow through the universe. An electron is actually a standing wave. It's not a point particle. It's not like a little planet orbiting a sun. It is, and at all times acts like, around an atom, a shape, a wave shape. It has a wavelength, it has a size and direction, but it is trapped. The difference is it is a three-dimensional standing wave. On a guitar, you only go up and down, or back and forth. But an electron has to go in all directions. And so the shapes are a little bit more complex, and the math tends to be a little bit more complex. So these are the types of waves and kind of how to consider them. Light is a traveling wave. It passes through the universe, where electrons are a standing wave. Well, wave behaviors, before we get into the specifics of orbitals, are important here. Because if you have one set of forces trying to pull something up, so let's go back to our transverse wave. If you've ever been on the ocean and two different boat waves, or on a lake or anything else, pass through you at the same time, you might get tossed all around, or you might barely even feel it if they both hit you at once. If I've got two waves, well, remember, the front here is telling any particle to rise. And so is this one. This, if I'm moving this way and I'm moving this way. That particle is going to feel the force of all the things affecting it. So if you have two waves trying to tell something to rise, they both tell it to rise. And it gets a double effect. The net effect is when you overlap waves, Well, the particles that are along it, in theory, these particles should just match the points along it. And so we can kind of draw a connection to the particles above. Hey, if this wave was passing through, they would spread out in a certain fashion. Well, if they're overlapped, they're going to spread out along it, except any that would meet where the two are, it gets a double effect. As soon as those two are both affecting it, what you really get is the sum of the two waves. So any particles that would fall on there will fall on the sum of those two, because these particles, they are feeling the combined effect of the rise of both waves. So your real surface is going to be this extra tall one. This is when you have constructive interference. Constructive interference is when the direction of the wave amplifies the effect. The two interact to create a greater rise than they normally would. Well, waves aren't really just one peak, though. Waves have rise and fall. Depending on how these align, if I bring them together, they'd be constructively interfering at the moment, but keep pushing them, and eventually you're going to get to the point where one of these is trying to push down right now, and one of these is trying to push up right now. Well, just as if you had two waves both trying to rise, the real surface would get a double effect. If you have one pushing up and one pushing down, you counter those effects. So if I had a bunch of surface particles, and we were to line them up, they'd be following the green one, but as they get to the middle, they're being canceled out. They're being canceled, and then they'd be able to follow the other end. If you were to look at your surface afterwards, you don't really get anything that looks like the waves at all. You get this mishappen double bumps on the edge, and as those two overlap with each other, well, the more precisely they are countering each other, the less effect they will have. If you are perfectly out of sync, the net effect is there is no change at all. Every rise is perfectly matched by a fall. Every fall is perfectly matched by a rise. This will look like there is no wave there at all. That is destructive interference. Destructive interference is when waves cancel each other. This can be partial or it can be total. But as any given point has a wave acting on it, if there's another wave, it has to take the sum of those two waves' influence. So this is why if two boat wakes pass under you, depending on if they're lined up or not lined up, you might barely feel it, or you might feel an oversized wave hit you. This occasionally happens on the ocean. If you're ever going along and then suddenly you just hit one really big wave, that is usually because multiple different waves happen to match up just right at that point to amplify themselves. Constructive and destructive interference are standard behaviors of a wave, and these are necessary for us to go into orbital discussions. And so we've seen transverse waves that can travel through things. We've talked about standing waves, where waves are trapped and simply oscillate. We've talked about interference, both constructive and destructive. These are properties of waves that we have to recognize in order to explain orbitals.